Okay, so now let's do an example that is 2D equilibrium of a particle. This is your first real statics example here. So far we've worked stuff that is vector manipulation, finding a resultant or breaking it up into components. But this is our first time that we have actually going to apply that stuff into a static situation. So we have here a system of cables or ropes or something, right? So they can only have tension in them. This is the simplest type of static system. It's the one we're going to get started with here. It's a 2D tension system. There is several members here, A, E, B, E, E, F, C, F, and D, F. They're all individual cables that are clamped, and none of these are continuous cables that all have the same force in them. There's no pulleys or whatnot in here. They're all like clamped there at E and at F and then at their other ends. There is a 50 kilogram weight here, which as you can see, I immediately changed that into newtons by multiplying by 9.81 because I need newtons, not kilograms. Okay, and the statics works on summation of forces equal to 0, not the summation of mass equal to 0, because that's rubbish. You know it. I know it. So let's not kid ourselves. Let's put it into newtons. Okay, so we have some geometry here. The other thing that's good to know here is that this is a spring constant of 42 newtons per millimeter, and this spring was actually stretched 7 millimeters to get into the configuration shown. So it's already been deformed. So that's going to be a good place to start, I think, is to look at what's going on over there by the spring and by that hanging weight, because those are the things that we know. To get into these problems, every one of them is going to be a little bit different, but this one here, I see that I know more about what's going on at E than I do at F. So I'm going to look at E, and to figure out what's going on inside, to find these tension forces, these internal forces, we have to make cuts. We have to make free body diagrams. And we're going to make a free body diagram first at E and then at F to solve this problem. And to draw a free body diagram, I state it with 3 simple rules. Okay. Once you've identified what you want to draw a free body diagram of, you do 3 things. One is you keep the part that you're keeping. So you figure out what you're going to cut, and then you keep the part that you're keeping. Step 1. It sounds very obvious, but you follow these steps precisely and they give you profound answers. Okay, so step 1, keep the part that you're keeping. Draw the diagram with all the parts you're keeping, all the geometry, all the angles in this case. An equilibrium of a particle, I need to see all the angles on my free body. Then you get rid of the parts you're getting rid of. Okay, get rid of all the other nodes. Get rid of F, get rid of, if there was something hanging at F, you would have gotten rid of it too. Because we're only keeping E. And then at the cut surfaces, we're going to put the internal forces that develop. Because these are fictitious cuts. We're not really cutting. And if we went and took some scissors here and cut through these cables, this whole thing would collapse. What we do is we isolate the system and we see what forces would need to develop inside to keep it in equilibrium. Because if this system is in equilibrium, all the component free bodies that could be drawn of it are also in equilibrium. So we're banking on that E and F are in equilibrium because we know the overall structure is in equilibrium. So my first free body, I'm just going to draw it here, and or at least identify what I'm going to cut. Okay, so I am going to be making cuts through each one of those members. All right, so when I make my cuts, I'm going to have a cut right there, I'm going to have a cut right there, and right there. All right, and let's go ahead and do it. So over here, I'm going to say free body diagram at E so that I know what I'm drawing, that you know what I'm drawing. It's all very clear. I'm going to come over here and identify node E, and I'm going to start drawing the parts that I'm keeping, right? I'm drawing a little nub of member, which is that right there, okay? And I am going to draw this little nub of the member over here heading towards F. I'm going to draw the nub of the member heading towards B. And I'm going to draw the nub of the member heading towards A. All right. And then I need to put the geometry that is happening here. And so what geometry do I have? Well, I know that the member BE here is at a 45-degree angle up there, which means it's going to be at a 45-degree angle here as well. So I can go ahead and identify that as 45 degrees. AE is horizontal, so that's cool. The weight is hanging down vertically, so I think that's pretty obvious. I do need to draw this angle over here too and identify it. All right, so to get that angle, I know that E and F, that F is 0.4 meters up and 1 meter to the right. So I can say that it's equal to the arc tangent of 0.4 over 1, which is 21.80 degrees. So 21.80 degrees. So I've identified all this. That angle is right here, 21.80 degrees. All right, now, so I've kept the part that I'm keeping. I've gotten rid of the parts that I'm getting rid of. I'm not drawing anything else on here that doesn't belong. And then at the cut surfaces, I'm going to put the internal forces that develop. Okay, so down here at the bottom, this is maybe the most obvious one. That cable hanging down from E, since the weight was 490.5 newtons hanging down, we actually know the tension of that cable is 490.5 newtons. So that one's pretty easy. I'm also going to have this one over here, which is going to be known. And this is member AE, and this is... so we can say T, why don't we go ahead and just call it TAE, the tension in member AE, where you call it TAE or FAE or whatever. It doesn't really matter as far as the variable names. Just write something so that you have something to write. TAE is quite simply 42 newtons per millimeter, which is the spring constant, times 7 millimeters of displacement, because that was given in the problem. Okay, and so 42 times 7 is 294 newtons, 294 newtons. So we actually know this, 294 newtons. All right, so now my last step is to continue drawing these vectors, and now these are truly unknown vectors. I don't know what they are. I'm going to call this one TBE, and this one here, TEF. So I've drawn them, I've drawn arrowheads, and I gave them labels so that I can identify them. So I'm looking at this free body. If you look, quite honestly, I don't have to look back at my other picture anymore, the overall structure, at least for now. I can work purely with this free body. It's complete. It followed the 3 rules that I was talking about, and I can actually use this and solve it. So I will now write my equations of equilibrium that develop at this free body. I'll put it right next to this diagram so that it all makes sense when I go back and look at my work and whatnot. So what can I do here? Every problem is going to be a little different. I think this one here, I have my 2 equations of equilibrium for a 2D planar particle. I can do sum of forces in the x equal to 0 and sum of forces in the y equal to 0. And I don't know that it matters which one I pick. My x direction is this way, by the way. So y will be up. I could do my y equation or my x equation first. It doesn't really matter because I have 2 unknowns in both of those equations. Let's just go ahead and do x first. Sum of forces in the x equal to 0. So I always write like this. I always say sum of forces in the x equal to 0. I know you might think that's a waste of time, but now I've identified, when I go back and check my work, I know exactly what that equation is. And my right arrow with positive is because, for now I'm always going to draw it that way, but I can change what I think is positive or in each equation just to help make the maybe less negative signs pop up. But anyway, I still just I'll always define what the positive direction is for the equation. So going to the right is positive as I drew this. Okay, so now let's look at this. I have the 490.5 not in the x. It doesn't have a component in the x. It's not going to be part of this equation. What it is going to be in this equation is going to be my TEF but only the x component, which is the cosine of 21.80. So TEF times the cosine of 21.8 degrees. And then I have, let's see, minus TBE, because the x component of TBE, let me just draw it real quick. It would look like this, wouldn't it? That is pointing in the negative x direction, so it's kind of a minus sign. Okay, so minus TBE times the cosine of 45 degrees. And what else do I have? I have that term right there, which is acting purely in the x, and specifically in the negative x, so I have minus 294 newtons. I write everything on the left side of my equation, and then I say equals 0. I don't try to put actions on one side and reactions on the other, because I'm just going to confuse myself and make a sign error. Draw your assumed positive direction, identify it, be clear about it, and then put everything on one side of the equation so that things pointing to the right are positive and things pointing to the left are negative. Set it all equal to 0 and then solve your algebra. So let's see, continuing this work, I would then have 0.9285 times TEF minus 0.7071 TBE, and I'll go ahead and move that 294 to the other side. I mean, I can move it over there now. I'm just saying, when you set up your equation to start off with, set it equal to 0 so everything is on one side. So let's see, solving this, I get, I'm going to solve for TEF. I don't think it mattered which one I solved for. It's two unknowns. I just have to solve for one, plug it into my next equation. So I'm going to do it this way. This is going to give me 0.7616 TBE plus 316.6 newtons. So that's the equation as it settles down being solved for TEF. Okay, so I'm going to hold on that for now. We'll use that in a second. Now I'm going to write my sum of forces in the y equation. Up positive. See how it's very similar to what I did before, and it's very clear, very easy to follow. Let's do it. So here, what's not going to be in there? 294. Not going to be in this equation because it doesn't have a y component. What does have a y component? TBE times the sine of 45 degrees is the y component of my orange vector over there. It's acting in the positive y, so it's positive. I'm also going to have TEF, okay, and that's going to be times sine of 21.80 degrees. Then I have 490.5 acting down, so minus 490.5 newtons equal to 0. Now, not only that, but if you see TEF here and you look at TEF here, I can sub this into that equation I just did for my x into my y and solve this system simultaneously. So this is where algebra comes into play. You could solve it, you could subtract one equation from the other, divide, whatever, the rules of solving systems of equations, whatever you like. I'm going to do it through substitution. Okay, so now I have 7071 times TBE plus now TEF. My equation from above, 0.7616 TBE plus 316.6 newtons. Whoops. Times the sine of 21.80 degrees minus 490.5 newtons equal to 0. And doing more work, I get that. Collecting terms, I have that. And solving for TBE, I get my first answer, 376.7 newtons. Now, If a free body diagram is not finished for you, if you think you need it for more stuff like we do in this one, I like to come over here and write what I have learned. So 376.7 newtons. So now I can look at my free body and have even more information. What can I do to finish off this equation? Well, I still need TEF here. And how can I get it? I can actually go back to my sum of forces in the X equation and get 0.7616 times 376.7 newtons plus 316.6 newtons. So TEF equals 603.4 newtons. These are all positive. They're all tension. Since they're positive, two things. One is when you draw these free bodies, always draw your unknown vectors pointing away from the particle, because that means that you're assuming a tension which is pulling on the particle. All these things are pulling at E. They're all tugging at E, wanting to moving it away. And so the cool thing about that is that if you want to assume that the internal tension force is positive, then always draw them away. And if you get a positive number, not only does it mean that you guessed right, but it also means that they are in fact tension. If you get a negative number, that would mean compression. Now, you should not be getting negative numbers in any of these cable or rope problems because, quite frankly, they can't handle compression. But we'll get into, when we get into trusses and all later, things have compression all the time, but not yet. So these being positive, they make a lot of sense. So now I'm going to, I think I'm done with that free body. I'm going to move on to my next free body. And if I can, let's try. Okay, I used E. Now let's look at F. And I actually learned something, right? That this tension in member EF was 603.4 newtons. So that rope, that cable or whatever has 603.4 newtons. That's wanting to pull at E up and to the right, like we learned up here. Well, guess what? When we're at point F, it's going to be pulling down and to the left. So when you go to the quote-unquote other free body or the other side, the internal force flips. And that's going to be true of all the internal forces we look at all semester, but definitely for axial effects, which is what we're doing here, tension and compression and things like that. All right, so just like before, I'm now going to say, let's draw our free body diagram at F. And so here is my node F. I've got a member going off straight to the right. I've got a member going up and to the right. I've got that member that we had before going down and to the left. Not only that, I actually know this value, 603.4 newtons, because I solved for it. I also know this angle right here. It is 21.80 degrees, because if this angle is 21.8, it certainly means that this one is also 21.8 degrees. So that's cool. Now DF here, we know it's going straight, so we don't really need to do any angle work. We already know it, but I do need to write my vector there. All right. And then I've also got my angle here to the orange line. And I picked this to kind of show you something interesting. If this is 0.3 tall and this is 0.4 meters wide, then what is this length right here? We know this to be 0.5 meters long. It's a 3, 4, 5 Pythagorean triple. All right, and that's really cool. You can find that angle by doing like the arctangent of 0.3 over 0.4, and I think it's at 36.87 degree angle, if I remember correctly. 36.87 degrees. That's great. I don't really like to think about it that way because Pythagorean triples are so neat. You can actually, if you write their values here on we call it a force triangle. So we have a 3, 4, 5 relationship, or 0.3, 0.4, 0.5, whatever. You get the picture. We can use this triangle instead of actually dealing with the angle, and it actually will save us some time. This only really works for nice Pythagorean triples, but guess what? Pythagorean triples happen all the time because we build these things and we build them to dimensions that we like as humans, right? We don't often go to weird angles, although sometimes we do, but oftentimes we don't. So we can use these. I need to give this its name, TCF. So this free body I think looked pretty good. I kept the part that I'm keeping, joint F, with all the angles that are shown on it. I got rid of the parts that I'm getting rid of. I got rid of the 50 kilogram or 490.5 Newton load that's over there at E. I don't care about that. I don't care about the spring anymore. That's all water under the bridge. It's all caught up in this number right here, by the way. But that number is that last step of the free body, right? At the cut surfaces, put all the internal force vectors that will show up. This one, we already know. These other two, we don't know their values yet. I give them names. I turn names into numbers because numbers are answers. Names are unknowns. So I like to identify what I don't know and then turn it into something I do know. All right, looking at this, sitting back after drawing it, saying, oh, that's a great looking free body. I'm very proud of myself. Since it's so clear, I should be able to see exactly what I need to do next. And, for equilibrium of a 2D particle, we have two equations of equilibrium. Sum of forces in the x equal to 0, sum of forces in the y equal to 0. And I tell you what, there's a good choice and a bad choice there. If I do sum of forces in the x, which is what a lot of people like to do first because x is first in the alphabet after, before y and before z, whatever, you should only develop that equation if it's the right one to do. In this case, it is not the right one to do because we would have two unknowns. We'd have the x component of TCF and we would have TDF itself. But if I do sum of forces in the y direction, I am going to be able to isolate TCF. All right? So I'm going to do that. I'm going to write my sum of forces in the y equation up positive. All right? Now, it was obvious in the last free body I did, but I just want to mention it. When you develop these equations of equilibrium, don't put in there like the the y component, like TCF sub y or something like that, because what you're really doing is creating a bunch of additional unknowns. Always write your unknowns in terms of this vector, in terms of the total vector, and apply the trig to it. So when you solve for it, you get the total vector. All right, it's what I did up above, but I'll just be clearer about it now. When I write this, I'm going to have 603.4 newtons, my green vector, times the sine of 21.80 degrees. And that is negative, right? Because that y component is pointing down, right? So I need to account for that with that negative sign. And then I'm going to have plus TCF times, and when you deal with a force triangle, you can look at the trig as being isn't the sine 3 over 5? The sine of this angle is 3 over 5, but we don't ever care what the angle is itself, what the actual number is at 36.7 degrees. I don't care because I know its sine is 3 over 5. So I just need to come here and write 3/5. If I wrote the sine of 36.87, it's fun. Try it at home. Put it into your calculator. Sine of 36.87 degrees. I guarantee you it's 0.6, which is the same thing as 3 over 5. Okay? Forced triangles, they work. Equal to 0. So then I can solve for TCF, and TCF equals 373.5 newtons, I believe. Let me double check that. Yes, 373.5 newtons. Again, in tension, I can come here, 373.5 newtons. Finally, I can say sum of forces in the x equal to 0, to the right positive, because why not? I then have, starting over here at the left, 603.4 newtons times the cosine now of 21.80 degrees. That is a negative term because it's pointing in the negative x. And then I have plus 373.5 newtons times now 4 over 5. Some people don't like forced triangles. If you're one of those people, that's fine. Write the angles. Determine the angle and then do the trig with it. These forced triangles are faster when you see them. Okay? But whatever floats your boat. Finally, TDF equal to 0. TDF will then equal 261.4 newtons. And ladies and gentlemen, we have now identified the forces in every single cable. And that is how you solve an equilibrium of a particle in 2D.